Hello. In this video, I'm going to be solving problem 2 from my students' practice midterm made available to them on Canvas. And for my students watching, this particular problem is one from version 1 of that practice midterm, available in the Files module. Files tab, sorry. And the problem reads as follows. Find a parameterization of the curve defined as the intersection of the hyperboloid given by this equation and the plane z equals x plus y. What type of curve do you think this is? Okay, so how do we begin with a problem like this, right? Generally, so when I see this equation right here, it's not immediately clear to me what a good parameterization might be. So one thing that's helpful, it's not guaranteed success, but it can be helpful in many cases, is to just kind of plug in the points and see if we can find some equations relating the coordinates at that point. So let me explain what I mean. So suppose P equals, so this is our points with coordinates x naught, y naught, and z naught. We're going to suppose that this is on the curve of intersection. And what I'm going to do is I'm going to see if I can get some relations between these three numbers that let me find a sort of obvious parameterization, if that makes sense. How am I going to do this? Okay. Well, this point, by definition, we said it lies on the curve of intersection, so the coordinates of this point must satisfy these two equations. So plugging in the coordinates, we get the equations x naught squared minus 2x naught y naught minus y naught squared plus z naught squared equals y naught. I'm going to call this equation 1. And we also get the equation saying that z naught is x naught plus y naught. Call that equation 2. So what stands out to me from these? Well, we can see that equation 2 gives us z naught in terms of x naught and y naughts. That's good for two reasons. So one, that lets us simplify the points or the coordinates on our point to just this right here. So notice now that we've expressed the z coordinate in terms of our x and y coordinates. And it's also useful because you might notice that if we take this expression here for z naught and we substitute it into the first equation, we get a nice relation between the two. So let me write this out. Substituting 2 into 1 gives the following. So we're going to get the same thing, minus y naught squared, but then we're going to plug in our expression for z naughts as this right here. This is equal to y naughts. But if we expand this term right here, this will be same thing plus x naught squared plus 2x naught y naught plus y naught squared. And all this is equal to y naughts. And what's awesome here is we get some nice cancellation between our terms. And combining everything else, well, we get 2x naught squared equals y naught. And what's interesting is, okay, remember our point P has, so far rather, has coordinates x naught, y naught, x naught plus y naughts. Again, because we just replaced the z coordinate with what it must be, x naught plus y naught, if it is to lie on the equation z equals x plus y. But But star, equation star here, lets us express y naught in terms of x naught. So now our point P is going to become x naught, and well, we see here that y naught is equal to 2x naught squared. So this is 2x naught squared, and then we get x naught plus 2x naught squared. And this is awesome because notice how now we have expressed this point P in terms of a single number, just the x coordinate of our points. And therefore, if we set that x coordinate to be t, we get the equations, the parametric equations, x equals t, y equals 2t squared, and z equals t plus 2t squared. And we can if we really want to be careful and like make sure that this parametric curve actually lies on our two surfaces, we can readily verify. Plugging these in to our two equations, x squared minus 2xy minus y squared, and then our second equation, x plus y, we can readily see that we satisfy these equations. It's just a little bit of algebra. Therefore, let me make this a bit nicer, my bad. Therefore, if I call this system, I'm going to call it dagger. Dagger are parametric equations. For a curve. And let's get a visual for what this curve looks like compared to the two surfaces that we have on Desmos 3D. So let's hop over there right now. All right, welcome back. So here is our Desmos 3D app. And let's see what our curve of intersection looks like. So just going bit by bit, let's first plot our paraboloid right here. As we can see, it's a paraboloid and it has two sheets. It seems to be opening at a diagonal, maybe, roughly in this direction. And then if we plot the plane right here is equals x plus y, we can see where the curve of what the curve of intersection is. It's just this boundary right here. And just looking at it, we might guess that it looks like a parabola of sorts. Proving this is a little tricky and not something I'm going to get into in this video because I think it's besides the point for the stuff I think is pertinent for my students' exam. If anybody wants to attempt to prove this themselves, you're more than welcome to, but I'll be skipping that in this video. And finally, we can plot the curve of intersection right here. And we see that it matches exactly with the boundary that was outlined earlier. And if we wanted to, we could hide the two surfaces and we see the curve more clearly. And again, it does look like a parabola here. All right, that wraps up this video. If there are any questions, please feel free to leave a comment. Otherwise, I will see you all in the next video.